first need to check whether this value, this key is already inside this dictionary or not. And to check that, we first need to try to find a node with this key, given key. And if P is already there, then we are going to change the value with the given value like this. Otherwise, we need to create a new node. And to do that, we need to find the position of the memory location using this hash function. And we can add a new node at the end or at the front. However, that depends on your choice. But in this implementation, I'll attach new node at the front of this position, all right? So what I'm going to do is I am going to create a new node with this key and value. And I'll put this node, this new node, at the front of this memory location, because this one simplifies the implementation. Okay, so this is this design choice. So you can just let's say data I is P, and while P is not none, you can travel all the way to the end of this linked list and attach this new node at the end. However, in this implementation, I'll just attach this new node at the front. Good. And let's move on. So we've talked about chaining. And this is one method of resolving the collision problem. And we implement it. And let's analyze the performance of chaining, the chaining dictionary. The running time of insertion is proportional to the length of the linked list in slot HX. Here, X is the key. If we have a really, really good hash function, then that good hash function will distribute all the items evenly, and the expected number of items is going to be divided evenly for each memory slot, memory location. So it is going to be number of all items divided by M, which is the size of hash table. And the number of all items can be U. And the expected number of, this expected number is called the load factor of a hash table. Thus, the expected running time is O lambda. However, our hash function, if our hash function was really, really bad one, and everything goes to just one slot, one memory location, and the running time of insertion is going to be ON. However, we are going to make our hash function really, really efficient, so that will not happen. And the running time of insertion is going to be, in average, O lambda. This is very simple to analyze. And the same analysis applies to search and deletion operations. So in the beginning of this class, I told you that we wanted to make our dictionaries O1, and we achieved this by using hash function. And the running time of insertion, search, and deletion is O lambda. And because O lambda is a constant, it is similar to O1. All right. So this is how we made dictionaries and sets efficient. And the second approach we can deal with the collision is using open addressing. So what is an open addressing? To define open addressing, we'll have a look at closed addressing first, and the meaning of open addressing will be clearer. So what is closed addressing? In the scheme of closed addressing, we can store items at the slot given by the hash function. So this one is what we use for chaining. We cannot store items at other positions than the hash function indicates. This is very fixed. In contrast, open addressing, in the scheme of open addressing, we can store items at a slot that is different from the correct slot. This correct means indicated by its hash function. So we are going to store some items that are not, not at the position that are indicated by our hash function, but some other places. And this one is one of the representative method of open addressing is linear probing. And we're going to have a look at linear probing here. So what is a linear probing? Let's say we have 10 memory slot, memory space, and our hash function is key, mod, or remainder 10. And when we want to insert 89, the remainder is 9, so it has to go to this position as follows. And next, we want to insert 18. And the memory location it has to go is 8 because the remainder is 8. So it's going to be placed here at this position. And when we want to insert 49, the correct memory location is 9th memory location. However, it is already occupied by 89. So we go to the next position, which is the 0th position, and put 49 there. So it is called linear probing. If this position is occupied, rather than chaining, we're going to go to the next position and put this item at there. And let's say we have 58, then it has to go to the 8th memory location. However, it is already occupied. So we go to the next position. However, that is also occupied. Then we have a look at the next position. It is occupied again. Then we go to the next position again, and it is empty, and we put 58 there. So this is how we insert some items like this in this linear probing. So at last, when we want to insert 30, it has to go to the 0th position here, but the 3 positions, consecutive 3 positions are occupied. So we're going to put this 30 here. So this is the scheme of linear probing, which is one of representative method of open addressing. All right. Okay. In the case of chaining, we used node class. However, in open addressing, we're not going to store or keep track of the next node. So we don't need this part. And we're going to define another class called entry. And this will store only key and value. We don't have to store other things. And as usual, as in the close addressing or chaining, we are going to use simple hash function. And let's implement dictionary again. First, we need to define the constructor. This is same as the previous one. Let's say we have 100 memory space. And we're going to define find key first. We're given key. We need to find the location of this key, okay? First things first, we need to find or calculate the memory location we need to have a look at. That is by using our hash function. And while self data I is not none, because this position can be occupied or not occupied, and our item could be at the next or next position, we need to have a look at positions neighboring to this memory location calculated by our hash function. So that is why we call this method linear probing. We linearly search or probe for the location of the key of interest. And if this position contains the key of interest, we are going to return true and I, because we have found this key value. Otherwise, we are going to increment I by 1 and conduct division method. Okay? And we do this until this position is not none. If this position is empty, we don't have to look at other positions. Okay? And we're going to return false and I. And at this position, we can insert this key value. That is why we define our find key method in this way. In defining the contains method becomes very simple once we implemented this find key method. We just call our find key method. And this find key method will return whether it finds the key of interest, like true or false, like this. And we just need to return found, like this, right? And the next method we are going to define is get item. We're going to call our find key method like this. And if we found the position, then we're going to return the value of the entry at the location. Otherwise, we're going to raise the value error like this. So this is similar to linear, this linear probing is similar to chaining, however, somewhat different. And we also need to define our set item method. This. And this is our second PPP exercise.